So the next speaker is Professor Jakob Stix from Heidelberg, and he will speak on Brauer-Manin obstructions for sections of the fundamental group.
Thank you very much for the introduction, and I'd like to take the opportunity to thank the organizers for inviting me and giving me the opportunity to speak here. And so my title, I recall, is Brauer-Manin obstructions for sections of the fundamental group. And so I'm happy that the audience is full of experts in Anabelian geometry and also in experts in the Brauer-Manin obstructions. So I'm looking forward to the feedback. Let me start by recalling the section conjecture, as this fits nicely into the topic of this conference. Of course, yeah, for this audience, I probably don't have to recall it, but as this is webcasted, then maybe it's anyway better to first explain what one's talking about. So let K be a field, and X over K will be a geometrically connected variety, and by X bar I denote the base change to its algebraic closure, and one should think of this algebraic closure of the base field as being fixed once and for all, so that sort of the structure of varieties of a K algebraic is sort of fixed. Now we have a fundamental group of X which requires a base point, and this base point should be a geometric point, but if it happens to be a rational point, then this carries a Galois action. And if you happen to have 2 points, then you also have, by the general philosophy of, well, the Tannakian philosophy, or in this case it's more the discrete Tannakian, so the Galois category approach, you have a space of torsors, a space of paths from one point to the other, which happens to also have a Galois action, and this is a Galois equivariant right pi 1 x bar. Now I'm moving to the algebraic closure. Torsor as is almost a tautology. So without this Galois action, this torsor is just a trivial torsor. Well, there's not much to say about classification, but the Galois action on it enriches the structure in such a way that those torsors become really different. So the variation with respect to these base points is enormous. So more precisely, let's say here we have the class of Galois K equivariant. And by the way, this is the absolute Galois group of K, so the Galois group of K algebraic over K, equivariant right pi 1 x bar x torsors. Then this is in one-to-one correspondence with a non-abelian H1. And this is also in one-to-one correspondence with a space of sections, which is abbreviated by sections for this extension. So let me say it precisely. So this is pi 1 x bar, conjugacy classes of sections, so splittings of the extension, which I denote by pi 1 x over k. So this is a relative pi 1 in some sense. And the extension is given by the homotopy exact sequence corresponding to the projection to the base. So you should observe that on the left-hand side, really, things depend on these base points being k rational. And otherwise I don't know how to describe the Galois action. Whereas on the right-hand side, we've lost track of the base points altogether, so I put that onto the carpet. This is, on the one hand, an advantage, but also an annoyance, because you have to work with these conjugacy classes of sections, because only those turn out to be well-defined. But this is a familiar feature also from topological fundament groups. So now this torso that we had here, in the case the base point is rational, gives you a class in here. And so this is associated to a rational point. And by this translation, you can also get a section which happens to be nothing but the functor of fundamental groups applied to the map which corresponds to this y. So we have spec k mapping via y into x. And, well, the fundamental group is only well-defined up to conjugation as a functor. OK, and yeah, in this business here, one is also forced to sort of choose universal signs. And how do you write the, whether this is a path space from x to y or y to x, and whether then the composition is by concatenation or by whatever, the other way around. So this is very annoying, and I can assure you most of the time it doesn't matter. And you can anyway translate from one side to the other. But I would be very grateful to discuss this once in a while, what is a nice and good choice of these signs. But anyway, it freaks me out most of the time. So I hope to avoid it. And I think it won't matter here. So what is now the leading conjecture of the subject for more than 25, 26 years now? So there's the conjecture going back to Grothendieck in 83 in a letter to Faltings, where he says that let K be a number field, and assume X over K is a smooth projective curve, genus at least 2, then he thought it's conceivable that the map associating a rational point, its section, is in fact a bijection. And the early hopes of the conjecture have been that this gives you a new approach to the celebrated theorem of Faltings on Modell's conjecture, which dates around the same year. But these hopes up to now have never realized. In fact, there's a subtle point at which so far any approach to this question actually exploits Faltings' theorem. So you run into a vicious circle. If you want to really give a new proof, then you have to find a detour at that point, and it seems extremely difficult. So let me mention what is known about this conjecture. And this is a particularly embarrassing because there's so many people in the audience who have contributed. So I hope I don't forget anyone. So I apologize beforehand for this might occur. So there's Hiroaki Nakamura, who contributed not to the projective version, but there's an analogous statement for open curves. And then you might have additional sections which don't come from rational points, but from rational points in the boundary. And so he classified those sections which I like to know cuspidal sections. And that was the content, or part of the content of his course earlier this month. Then there's Akio Tomogawa, who contributed to another variant of this, which was unexpected, namely, let's say K is a finite field. And of course, then the Galois group is free, and you have lots of sections. But he was able to describe explicitly which of those sections come from point. And as an amusing exercise here, I would add that that was not known to me for a long time, but I didn't realize it until a lecture by Mohammed again. So that if A of k is an abelian variety, then the section conjecture holds. So k again is a finite field. So k finite. So although this finite field has a free Galois group and there is an abundance of sections, it turns out that most of them are conjugate. And so you cut down again to a finite set, which happens to be exactly the set of rational points in bijection naturally. Okay, more is true, namely there's work by Mochizuki on actually the home version of Anabelian geometry for smooth projective hyperbolic curves. And if you go into the details of his proof, you realize that actually what he has to do, has to prove is a refined, so he has to answer a refined question about sections of the fundamental group, but not for where the field is a number field, but is a p-adic local field, which is in some sense non-constant. That's one part of his contribution, but the contribution I want to mention here explicitly is that he gave an Anabelian proof for this map to be injective. And injectivity was known already at Grothendieck. You can derive it from the Kummer sequence and essentially something like weak model Weyl. But Mochizuki's proof is nice because it features sort of an interplay between Anabelian results. So the statement is that if you have an isom version for Anabelian curves, and you need the curve you want to prove the injectivity of the section conjecture minus 1 point. And maybe some tricks if there's an automorphism group. So if two sections agree, then by pulling back the universal action in the family x cross x minus delta over x, which gives you the monodromy on the curve x removed 1 point, then if you pull back this universal action of the base by the sections induced from points, then you get, if the sections agree, that the corresponding outer Galois representations agree. And then the Anabelian results I'm alluding to says that then the curves agree. And so x minus the 1 point is isomorphic to x minus the other point. So if the curve has no automorphism, that gives you that the points agree. And although this, of course, as a machinery is much more involved than the application of the weak model Weyl, I sort of like this argument because it stays in the realm of Anabelian geometry in order to give an argument for it. And
are you sure the other argument requires only weak model? Yeah, I'm very surprised by that. We need model base. And allow points to be divisible. Weak model base has nothing about it.
Yeah, so okay, you're right. You're right. So you need the model Weyl theorem. Okay, the advantage of Mochizuki's approach is that whenever you have an Anabelian isom result for these curves, then you get the injectivity. And in particular, because his version for Anabelian geometry is pro p, geometrically pro p, you get also the injectivity of geometrically pro p sections.
One comment about that. That's what's interesting about this problem.
Yeah.
Model Weyl requires height. Weak model Weyl would.
Okay, so then I would also like to mention that there are birational versions. And that prolongs the list of people who have contributed to Königsmann. Jochen, do you write yourself with an Ö or with an OE?
OE is fine.
OE is fine? Okay. So this has to be underlined because so birational version refers to that you take a, well, first of all here you allow your curve to be affine, and then you take the projective limit over all neighborhoods. So you're actually dealing with the corresponding extension for the absolute Galois groups. And then of course, the injectivity doesn't hold anymore because you run into this problem that each cuspidal section gives you actually a package of sections of uncountable cardinality, but nevertheless you can control them. And so he proves that over a base field which is finite over the p-adics, actually every such section comes from a rational point. And I would underline this because this really is an existence statement which is different, fundamentally different from the other ones. So this is really a very big achievement. And Florian Popp has worked on some minimalistic versions of the section conjecture. And I would also like to mention that Hélène Hénault, together with Olivier Wittenberg, have work done in this context where they, in particular, do what the algebraic geometers usually want to do if they get a result which depends on logic. They'd like to kick out the logic, so sorry for that. But they managed to give an algebraic proof of Königsmann's result. Okay, and there are even more names, namely Hélène Hénault has worked with student Hai, and myself computed. David Harari and Thomas Samueli have contributed. Jordan and Kirsten Wickelgren. Then the workshop we had in July, there was Mohamed Saidi, who has reported on joint work with Akio Tamagawa. And there's Yoshio Hoshi, who will probably report on work he's done with Mochizuki on the section conjecture. And there's also Richard Hain, who has given a talk about this. So there's really a lot of people who have already contributed, and I hope now I have anyone should scream if I have forgotten him. Okay, so what is known is that by a strategy which goes back to Akio Tamagawa, a weak version of the section conjecture is actually sufficient over, let's say, number field or p-adic local field. So, okay, a number field or k over q p finite, then a weak version of the section conjecture, namely that if there's no point, then there's no section. Oh. This is actually sufficient. And the quantifiers here go that you need that for all covers of X. So it's not just one curve where you need this weak version. And also, this is the step where you invest the model the model Falting's theorem. And it turns out that actually to produce examples for the section conjecture by using the statements, so giving examples where you're sure that there's no section of this extension is embarrassingly difficult. And let me.
You define an extension only in the case when there is a reference.
Sort of, not exactly, because here I kicked out the base point, and you need the base points in order to make these two things happen, but the right-hand side is independent of it. Yeah, and it turns out that the case which has no point is sort of the key to the matter, if you want. So, yeah. Yeah, I borrowed this from Ted Chimberg, so I should pay due respect.
Actually, in a sense, you don't actually need a point to make sense of it. You only need a section.
Yeah, that's true. That's true. Yeah, and I've thought a little bit. You can rephrase this by saying that a section itself is a valid base point. Yeah, and then you could try to study more systematically the fundamental group of base point in that section. Yeah, but once you pass to this picture, then you lose this again, and so I'm not really certain whether this actually helps this viewpoint. But it's a try. So let me elaborate here on this weak section conjecture a little bit. Namely, there's a more or less straightforward theorem which says that this is true for genus zero curves. So U over K is a number field, let's say, and the genus of U is 0, and U is hyperbolic. which means that it's Euler characteristic 2 minus 2g minus n, where n is the number of boundary points. So the degree of the boundary divisor, this should be negative. In other words, this is at least removing 3 points. Then the following is true, namely pi1u, or let's say u over k is non-empty. So there are points. This is equivalent to the section splits, the extension splits, and this is also equivalent to the abelianized extension splits. And if you get this statement and you want to prove it, you probably have no difficulty in doing it. Yeah. So it essentially goes down to analyzing the Como sequence for torsors under tori, and then realizing that there's no maximal divisible subgroup because you have Hilbert 90, which kills all the torsors after some bounded finite extension. And so that gives this result. Okay, from I think it's not, and I just wanted to be on the safe side, maybe. Yeah. So. Say again?
I mean, I have no idea. I'm just asking.
Let me think. No, I think you don't even need this. So yeah. Of course, the case of genus 0 is especially easy because once you know that the compactification is not a form of P1 but P1 itself, then any open will acquire points because there's just an abundance of those. So this is the part which makes it easy. Okay, so there's one result which I skipped here, namely Mochizuki. Elaborated in around 2000, previous work by Sullivan, Cox, and Huysman to derive the real section conjecture. So this is now a theorem, the real section conjecture. And it claims now whenever you have a hyperbolic curve over the reals, then a real point, of course, gives you again a section, but even more is true, namely 2 points in the same connected component give you the same section, but then this is indeed a bijection. So if you have no real points in particular, so x over k, some real place, and no real point, then you'll know that in particular you don't have a real section, and therefore you cannot have a section. For that, I'd like to stress that we have a notion of functoriality for these sections. So if k over capital K over little k is an extension of fields of characteristic 0, then the geometricity of the fundamental group says that the projection from the geometric fundamental group over k to the fundamental group over x, this was the one that was denoted x bar. So this is in fact an isomorphism, making the extension of the base change x over capital K a pullback of the extension of over little k. So pi1 xk over k is a pullback of pi1 of x over k. And then, of course, you can pull back sections, which gives you a map from the section space of x over k to the section space of xk over k, which, in order to allude to the notation that we want to have, I denote by the section space, but capital K rational points of it. So trying the strategy in making the notation closer to the notation of rational points for a curve to come closer actually to the proof, which of course is only psychologically and doesn't contain any real math. So S maps to its base extension, which is just using this pullback structure of the extension. So this goes into the thinking that once you have a real place but no real point, then well, a section would induce a real section by this machinery, and then you get your contradiction. So then I came up myself with a theorem studying obstructions at a p-adic place. So you know, K over QP some finite extension, and let's say so X over K again smooth projective genus at least 2. Then assume that the pi1 extension splits. Then we have that the period of X, which is the order of the torsor of line bundles of degree 1 in H1K of the Jacobian, is a power of P. And also, and the index of X, which is the GCD of the degrees of the residue field, is also a power of P. And these agree. Except if P is 2, where we need an extra assumption, namely that there's exists a cover below. So this is unusual. So X should itself be a cover of something else of even degree. Okay, and shortly afterwards, so these two results, namely the real section conjecture and also that a section locally imposes strong numerical constraints on period and index, can be used to produce an ample supply of examples where the section conjecture is true for trivial reasons in some sense, because both sets are empty, and there's a local obstruction. So luckily, because this was an omission in my result, in my discussion, there was a theorem by Harari and Samueli who managed to, with the help of Flynn, Victor Flynn, to produce examples where actually there's a violation of the Hasse principle. So their example is X over Q, and the Jacobian of X should be isogenous to a product of elliptic curves, and these elliptic curves have infinite Monod group and finite Char. And also X should have a local point, so an endelic point. And but no degree 1 zero cycle over K, of course. Then they could prove that the extension does not split. And even stronger, because, well, this result is morally concerned with zero cycles, so an abelian setting, and therefore they were able to show that the obstruction to being split comes, in fact, from the abelianized extension, which I'd like to denote here by simply adding an abelian, and that means that I push the corresponding extension by the characteristic quotient, which is given on the geometric pi1 by its abelianization. Yeah? So even that smaller part actually is sufficient to realize that the extension is not split. And that gives me an opportunity to.
In your theorem too.
Say again?
In your theorem too.
I just wanted to say this. In fact, the statement that the period here is of order power of p also depends only on the abelian quotient, but it's not the same for the index. So the index, and therefore I like this statement still, although this is of course a much stronger example. It is, in order to get also the index a power of p, I required a slight subtlety. So I should probably confess that an important ingredient into the proof of this theorem is the result by Lichtenbaum and Roquette that the index is in fact so the cyclic group of order the index is isomorphic to the kernel of the restriction of the Brauer group from k to x, and so Lichtenbaum duality enters the picture, but and also Lichtenbaum had congruences relating the period and the index, and they play an important role. In particular, he shows that period and index can at most differ by a factor 2. So what Tamas just said is that you get a value with almost the abelian part, namely the period equals the power of p part you get by the abelianized. And then the index is it's a power of p times 2 maybe, and you want to get rid of 2. And for that, I needed quotients which are of the form, so here you have the top quotient is abelian, and then you need 2 abelian below. So it's slightly non-abelian, but not too much. But at least it is. And there are counterexamples where you have an abelian section, but no section for the full thing, namely for genus 2 curves, which happen to have period 1 and index 2. So over a field which is not over Q2, of course. Then. Right. So now I need to erase. So now I've explained the fundamental group extensions and also in abundance what is known on the section conjecture. Well, I don't summarize what you can see by looking at the web streams from the previous conference and the talk of Mohammed about the section conjecture. So I'm not competent on this. But let me say that from my title, of course, there's so far no reference to Brauer-Manin obstructions, and I should change this shortly. So if you want to speak about Brauer-Manin obstructions, one has to look at Adels. So K is now a number field, and A over K is the ring of Adels of K. And then we'd like to know what is an adelic section. So right, and I have a definition for which goes the following. So pi1 x over k, and then coefficients in the Adels. This is defined to be, of course, a subset of the product of sections for each completion, and it is a definition which is sort of, well, I'm willing to negotiate the definition, yeah, but there's sort of a lower bound and an upper bound for that definition, and what I can give you exactly works, so I'm happy with it. So a lower bound, of course, is that the diagonal image of the space of global sections should be contained in the adelic ones. And so let me now give the definition. So a tuple of local sections S sub V is adelic if for each homomorphism from the fundamental group to a finite group, almost all, so all but finitely many, composites, so the corresponding local so we have the local Galois group mapping via the section to this fundamental group, and then we compose it with phi to G. So this is the map from Galois KV to G. This describes a field extension of this local field, and this should be unramified for almost all of these places. Okay, so this is just a suggestion. And so maybe you feel that the quantifiers don't really match the right way. So you should have maybe that in adelic section, well, first you single out a finite number of places where you allow ramification. Then for all these quotients, you should have that. But then you're getting into trouble when the residue characteristic enters in this group G. And so I'm more happy with this definition. And for the purpose of the Brauer-Manin obstruction I'd like to present today, this just works. So I'm happy, and that's fine. So let me quickly review the classical Brauer-Manin obstruction. Going back to Manin, using the Brauer group, therefore the name. And it was mentioned already in the first talk by Goethe-Universität, but let me remind you that here you take a Brauer class over X, which by definition here is H2 et al. With coefficients in GM. And then that allows you to describe a function on adelic points. And there's a dot saying that we take only the connected component, the set of connected components at real places, which I was told goes back as a notation to Björn Bonen. Is right? Is that right?
Yes, so.
Okay, so I think by the end of the talk I will have everybody in the audience attributed something. Say again?
Just as good as Cardiac symbol.
Okay, so this maps to Q mod C by, so a tuple of local points gets the sum over all places, the local invariant map, which maps the local Brauer group into Q mod C, and you pull back your class via that point. So because you're dealing with adelic points and your class is unramified almost everywhere, almost all of these are 0, and this is actually summable. Now, the theorem is that the diagonal image of the global points will end up in the so-called Brauer-Manin kernel, which consists of those adelic points such that this pairing is 0 for all A. And the reason for that is one of the main ingredients of global class field theory. Namely, we have the Hasse-Brauer-Noether exact sequence relating the Brauer group of a global field to the Brauer group of its completions. And here exactly this map summing over all the local invariants occurs. So, and this is exact. Now it's a one-line proof to see that this diagonal image is in fact in this Brauer kernel, because if you happen to have pullbacks along a global point of a global class, then these local components here are the local components of some global Brauer element, and then this evaluation dies. Okay, so now the natural reflex in the section conjecture is whenever you have a result for rational points, you want to have it for sections. And that's what I'm doing now. Of course, there's a difficulty because these Brauer classes are defined with respect to the sheaf GM, and the fundamental group is not really knowledgeable about GM, but it's knowledgeable about its end torsion. And so we're looking at the map B from second cohomology of X with coefficients in mu n, which always injects into the second cohomology of X itself with mu n. If X happened to be a k pi 1, or you can relax this in, well, you only need it in degree 2. But anyway, so if it's a k pi 1, this is an isomorphism. And in particular for curves which are different from the projective line, this is an, or forms of the projective line, this is an isomorphism. And then we have a surjection further to the end torsion of the Brauer group. So you see, a class in here might be lifted to a class here. And in fact, because the Brauer group, let's say we have a smooth variety, then this is torsion. Any class, in fact, comes from such a cohomology class in degree 2 of mu n. Now, on the space of sections, you can now mimic the above definition and defining a pairing with that class. And for that reason, it was very good to introduce these adelic sections, because now this is sort of an upper bound for this set. We want this function here to be well defined. So what does it do? A tuple of local sections, you assign the sum of all places, the local invariance of its pullbacks of this class. And now why is this summable? It's a very quick argument. So this alpha corresponds to an extension mu n to e alpha of pi 1x to 1. And because this is a profinite group, this is continuous cohomology, this is induced by via some phi and inflation of an extension of some finite quotient. Now, here you have your collection of local sections, and this local contribution is trivial if and only if the composite down there can be lifted to E. Now, almost all of these are unramified, and so if unramified, therefore this composite factors over a free group, namely the Gallo group of the residue field, and then you can lift it. And in such a way, you see that in fact, this local contributions are almost always 0. Yeah. So this gives a well-defined map. And now, so those were the constraints that I needed for the definition of adelic sections to be reasonable. I wanted them big enough so that I should mention that I wanted them to be big enough that they contain the diagonal image, but it should be small enough so that I can actually sum these local obstructions. And maybe another remark which fits in here is that this is in fact equal if x over k is projective. It's also a good feature of the definition, because this should, of course, be true. Okay, now I hardly dare to call this a theorem, because again, the proof is not complicated. It's the same one-line proof here, namely that if you take the global sections and map them diagonally to the adelic sections, then you end up in the corresponding Brauer kernel. So this is the tuple of local sections such that whenever you pair with whatever class, you get 0. And the proof is exactly the same. Yeah. So once your pullbacks here of this global class are by a global section, then these are in fact the local components of something global, and then the sum dies. Yeah. So it's only that I like the statement, and it's an analogy to something classical, that I'd like to call this a theorem, but the proof-wise, this is just trivial.
So the original one you said, x was projective. And the statement you gave here was a Brauer group. Otherwise, the sum did not be finite. I mean, you have the same problem. You see, you put this condition in order for open varieties, in order to be able to have a finite sum. But here, if you take an open variety, I don't see why. I'm pretty sure, in fact, there are counterexamples that if you take another Brauer group, it will not vanish. I'm talking nonsense. Sorry.
Yeah, because I'm taking a class in Brauer X and so on.
Okay.
Okay. Yeah. Thank you.
Yeah,
That was
sorry.
too intimidating. I
What
wanted
happens
to
when
correct it.
what happens when x is projective is that for a given element there's a uniformity on the V's where it vanishes.
Yeah, exactly. And this is going to show up. Okay, so now there's, of course, the following diagram. You take your global points, you map it to adelic points, and which are not Brauer obstructed, and you map them to all adelic points, and then you have here the evaluation with that class mapping to Q mod C. Now, by the injectivity of the section conjecture, so this goes into global sections, now diagonally mapping into pi 1 of x over k adelic Brauer unobstructed, mapping to adelic sections, and here you have this evaluation by alpha, and if we take alpha, b of alpha to be a in the sense of the map above, then it's clear, almost clear, well, it's clear that this actually commutes, and one can show, I should have said that adelic points here map also to adelic sections. This was probably not clear right away, but this is true. And now because this B map is surjective, in the cases where we have k pi 1s, you get here a fiber product, so if B is surjective. And even more is true, you get a fiber product here if the Brauer-Manin obstruction is the only one to rational points. Yeah, then these two facets are in fact Cartesian, and that allows you to actually deduce the section conjecture from the local section conjecture. So if you admit this, so there's the following theorem saying that the local section conjecture plus the Brauer-Manin obstruction is the only one to existence of rational points, then you've got the section conjecture over number fields. So by the local section conjecture, I mean the section conjecture over finding extensions of QP. Because of the reals, we already have it. Yeah, and the striking thing for me is that people actually believe that this might be true. Isn't it? So there's evidence by thesis of Sharashkin and also Stoll and Funen and Molov. He reported on this during this conference. So this might mean that we actually have a path to prove the section conjecture over number fields by just doing the local section conjecture.
Also here, I guess you have some statement for a single curve. Right?
Not exactly, because this result here would always give you only the existence of points. So you would get the weak section conjecture. But in order to deduce from the weak section to the full one, you need it for all covers. And then you're again in the mess of controlling all curves, basically. Because how do you single out those curves which are covers of a given one from all the other ones? So I think, yeah, one is tempted to think that there's a chance to prove the second conjecture in the case where there are points for specific fields.
I mean, aren't there versions of this statement that, I'm trying to remember what Felipe said. I mean, there's versions of this statement, Brauer-Manin obstruction is the only one that actually try to pick out for you the rational points, right? I mean, I'm trying to remember. Three in Belloch's talk is what I'm thinking of.
Okay, let me try to present you one example and then elaborate more on this question. Because it's very nice that the chair of this session is Professor Goethe-Universität, because then I can thank him for having explained to me the Brauer-Manin obstruction to the Reichert-Lind curve in Oberwolfach this year. And so I use that now to present the following theorem. So the Reichert-Lind curve is the curve given by the equation 2y squared is c to the 4 minus 17. And I want to have an affine curve, so I assume y is different from 0. So this is a curve of type 1, 6. So genus is 1 and 6 boundary points. And I can prove the theorem that pi 1 u over q does not split. And the more precise version, which is unfortunately again disappointingly abelian, is that pi 1, its completion, so this is, no, bars is bad, so x, let's say x is a smooth completion. So this is now the pi 1 of an elliptic curve, so this is inherently abelian, does not admit a section such that locally at 2 and 17 we have lifts of the following kind. So you have pi 1 of x, and in fact we only need the geometrically pro 2 part here, because the obstruction will lie in a 2 torsion class. And we lift that to the pi 1 of the open curve, which is abelian and pro 2 geometrically. And so here we have this section, and locally at these places v, which are either 2 or 17, we need a lifting to this open part. The reason for that is that we need y to be different from 0. So we want that y is a unit. And let me quickly tell you how that works. So the class that I was so grateful to know is the class alpha, which is a lift of the cup product of 17 with y. So those are classes which live by the Kummer map in h1k pi 1 u, nonsense, h1 pi 1 u mu 2, and their cup product lives then in h2 pi 1 u mu 2 tensor 2, which luckily is also mu 2. And now with that lift we get the following computation. Get this correct. So the pairing with whatever local tuple of sections is the sum over all v's, local invariance is v upper star alpha, and it turns out, due to good reduction outside 2 and 17, we only need the places 2, 17, and infinity. Because all the other ones automatically give 0 contribution. Now, at infinity, we have the real section conjecture. At 2 and 17, we have assumed this lifting, and therefore we are able to use this cup product decomposition for the class. And the cup product behaves well with maps between cohomology. We've come from maps of sites. So this is contribution at 2, 17, and infinity of the local invariant of, well, the pullback of the class of 17 is again 17, because this comes from the base. And now you have to evaluate this unit y into in the section as v. By that I mean that you use Kummer theory to actually map a function into a class h1 pi 1 u mu 2, and then you pull back, and that gives you the value of that guy at the function at the section. And of course, this is not a plain value in k, but it's a unit of it's an invertible element up to squares. And if you replace mu 2 by mu n, you get values in these quotients where 2 is replaced by n, and in the limit for a certain completion of this k star. But here we get along with knowing the value just up to squares, because this happens here in this two torsion point class. So 17 is a square at 2 and infinity. So this gives just the contribution at 17 of 17 and y of s17. And this happens to be just 1/2 for the following reason. Although it looks like this evaluation does nonsense with respect to this equation has the form, it's a multiplicative equation. It's 2 times the square times, and this is a norm from a field extension. So when I claim that we have 2y s17 squared equals a norm from q17 adjoint 4th root of 17 over q17. And now what you have to evaluate is c minus 4th root of 17 at this section, and then take the norm. Yeah, the norm is a product of Galois conjugates, and the action of Galois is sort of preserved by evaluation of this section. So this is compatible. And therefore, evaluating of a thing which is a norm, again, gives you a norm. And luckily, this is now all you need in order, with local class field theory, to deduce that this value is in fact 1/2. Yeah, you play around with norms from this. This is an abelian extension of degree 4. You take the and cyclic. You take the intermediate extension, which is q squared 17 over q17, and this is non-vanishing if and only if that guy is not a norm from that extension, and this you can deduce from this equation. Okay, so this is an unconditional example where, again, we know that the section conjecture is true for more involved reasons, namely really being able to compute the Brauer-Manin obstruction in terms of sections. So I have to confess that there's also a part of defeat in this story, because for some time during this month I tried to copy this proof and apply it to another case, a very classical case where we know that there's an adelic point but not a global point, namely the case of the Selmer example, which is so 3x cubed plus 4y cubed plus 5c cubed equals 0. And I didn't manage to find the right Brauer-Manin obstruction to actually prove that there's no section. And at the end, so classically it's enough to use here a locally constant Brauer-Manin obstruction. And if I try to use that one and play it against local sections, I think I'm now pretty much convinced that there are adelic sections which survive this Brauer-Manin obstruction. So this is in fact maybe also a direction to let one doubt whether the section conjecture should even be true. So, but this is work in progress. And yeah, I think my time is up, which is unfortunate because I wanted also to talk about the descent obstruction, which is of course a natural cousin of the Brauer-Manin obstruction here. And then I would have the pleasure to also mention Skorobogatov and Harari and the student of Harari and Demarche about what is known about the interplay between adelic sections and their descent obstructed and Brauer-Manin obstructed subsets, and then coming in the end to a theorem which says that in fact if this descent obstruction by finite état covers is the only one, then in fact the local section conjecture together with this statement implies the section conjecture. Of course, well, this is a stronger assumption than thinking that just the Brauer-Manin obstruction is the only one against the existence of rational points. But even then, the section conjecture would imply, so the section conjecture over global fields would imply that this finite état descent obstruction is the only one to rational points. And so tying those questions more intimately together, which shows that those two apparently different strands which are present here should work together to think about the section conjecture. Thank you very much for your attention.
So I want to understand? Can I just understand what you were saying about what you believe is the case about the Selmer curve? Do you think that there are adelic sections which are not Brauer-Manin obstructed, even though?
So there is a specific Brauer-Manin obstruction, and so if you're looking at those Brauer classes, which if you go to the local curve, so over a p-adic field, then become constant classes, so coming from below. So this is the group which surjects onto the Teixeira-Farevich of the Pk variety, and is the player if you want to exploit the Cassel-Tate pairing versus the Brauer-Manin obstruction, and seeing that this is in fact sufficient for seeing that this guy dies or does not die. So in this case, you should be able to, well, everything is known about this curve. Yeah, having global points is in fact obstructed here by one of those classes. So I was able to compute that class and trying to see what it does with sections, and it turns out that well, the trouble is here to actually compute the local contribution at 3, and you're working with a 3 torsion class. So there's 3 and 3. Whereas here in this Lint curve, it was, you have something of 2 torsion and the trouble comes from 17. So yeah, this is a tame situation, and the other one is just wild. And I'm very much convinced, but I haven't checked it again. So after I was convinced, I left it on my desk and I will come back to it later.
Are you saying that locally at 3, you will get more classes by evaluation that you would get by evaluation on the rational points?
You have more sections. You have more adelic sections.
And you get more values.
I think you have more 3-adic sections than.
No, okay,
than
that
just
I can
points.
believe. But then when you evaluate the element in the Brauer group which you have, you find more.
You find everything.
You find everything.
That's the problem. Yeah. So from the component at 3, you sort of can destroy that the Brauer obstruction is contradicted. So this is not carefully checked, but I feel that this is true.
Yeah.
Concerning your result over p-adics, that the existence of a section implies that period equals index is the power of p. So if one wants to prove the section conjecture over p-adics, one would like to show that this is equal to 1, of course.
Of course, yes.
But if you take neighborhoods of the section, do you know if it is possible, for example, to prove that if you take all the neighborhoods and you look all their periods indexes, that these are bound?
Which would of course mean that their index and period is 1, right? If the index and period is bounded, then it's 1.
The neighborhoods of the
section?
Yeah.
Well, we can discuss this. I thought a little bit about this, or a lot about this, and I don't know. So there's some interesting insights into that problem, but nothing definitive. So yeah.
What was the question?
The question is whether, so when the section conjecture is true, then of course period index should be 1.
Over p-adics.
Well, over whatever field it's true. If there's a section, then there should be a point, so period index should be 1. And over p-adics, the natural question would be to see whether one can improve my results to actually getting index and period is 1, or Morgan was asking if you look at the neighborhoods of that section, whether you can at least bound the period index by some uniform upper bound among those. And my immediate reaction was that I know that in this case, if you can bound it, then it's in fact 1. And but I have some ideas about it, but I cannot prove it. So that's bad.
Concerning this, that the local section conjecture plus the Brauer-Manin obstruction is the only data implies the section conjecture that uses actually faultings.
Oh yeah, of course. It uses faultings. Well, he's an honorable mathematician, and the theorem is certainly true, so I think it's allowed to use it, or?
I want to prove.
And there's a student of him in the audience, so I shouldn't say anything bad. And I can't. So.
Feel free, I won't tell.
No, I don't understand. No, I don't understand. Why they should use faultings the last?
Yeah.
Because from here you only get existence of points, and whenever you use the result that existence of points is sufficient to prove actually that there's
Okay.
yeah, you
I don't know.
already
You mean
already
to get
used
the
yeah, faulting enters into the game at a very early stage.
no, you mean to get the strong section conjecture?
Yeah.
Not the weak.
Yeah. Of course, you could imply here also maybe versions where you ask not just this being the only obstruction to the existence of rational points, but being the true obstruction which cuts out all global points, so having weak approximation. Yeah, so this is not a definite talk. Yeah, so you can modify versions which you don't like and improve it here and there. So, but this is the overall picture, and of course I think it's striking that the logic is there, that something which is believed and the local section conjecture would imply the global section conjecture.
I have a comment on this statement. I mean, so was it known before last December? Because Wittenberg sent me a letter explaining this implication, so that's why I'm asking you. This one, this implication. Or is it in the air, or with,
What's in Scholl's paper?
So it was in the air for, the essential ingredients of that I have since 2005 at least. And so I met Olivier in November, and we discussed about this, and so yeah, this is an omission. I should have said that part of this Brauer-Manin obstruction, we never openly discussed about this, but we sort of started to discuss, and then immediately we thought we know both about the topic. So I should say that this was independently also discovered by... No, I agree. Yeah. I don't think that I'm telling you rocket science, but this is... it's still a striking
I mean,
thing
I kind of
that
think
should
Scholl
be known
also
to
knows this, is that right?
a wider
Before he
audience.
goes in better.
I have another comment about this, but maybe we can discuss later, because I have a non-Abelian version of this last statement, maybe more precise, but maybe this is also the statement that you get with descent obstruction.
Yeah.
So maybe we can
I'm
discuss
pretty
it.
sure that this is the same. Yeah.
Okay, well, maybe you can discuss that later.
Yeah.
Okay, so any other type of question? Okay, well, let's send the speaker.